Welcome back. Um, if you can consider one day off as being gone. Um, any general questions or problems? Um, I didn't mention it in my email yesterday, but I'm currently down to 350 papers to grade, so I'm hoping to get them all done by the weekend. Um, the project papers are my number one priority because I want to post project two shortly, but I want to make sure you have feedback on project one before you start project two. Unfortunately, those are also the papers that take the longest. So I think I'm down to 170 of those. So since I can only do 8 to 10 an hour, you do the math. You know, but hopefully by the weekend they will be done. Um, any other issues? Okay. We were talking about this problem at the end of Monday, and we sort of half got through it. Right. Again, it's much like the first problem we did on Monday, right? Except in this particular case, the amounts that were given include both an initial and a final amount, right? And so, as I'm fond of saying, all equilibrium problems have three parts. I told you I will say it 10 times a day. Today is no exception, right? And again, the first and most important part is the balanced equation because really the second and third parts stem directly from that. This was my good old usual water reaction. The K equation is like so. And then my ice chart allows me to keep things organized. It also, in some sense, guides my solving problem, right? As I'm filling in the ice chart, it's really identifying the things I know and the things I don't know, right? And to some extent, right, my ice chart is nothing but a grid of things I need to know, right? And so I potentially need the initial amount of hydrogen. If I don't have it, that tells me that that's what I'm looking for, right? If I don't have the equilibrium amount of water, that's what I'm looking for, right? In this case, I was given three amounts, but again, they actually correspond to two completely different time frames, right? I had the initial amounts of hydrogen and the initial amounts of oxygen, and then I was given the equilibrium amount of water, right? In some sense, this is a fake, but otherwise perfect example of how this experiment might go if I was trying to determine the equilibrium constant, right? Because what I have is the initial amount of the reactants I threw in the beaker, right? And as I'm fond of saying, you have to be really lazy not to know that, right? Because you determine what goes in your beaker, right? And so if I weighed them before I threw them in my beaker, I should know what the initial amount of the reactants are. Ultimately, right, this is really a general rule. If I'm trying to determine the equilibrium constant, I need to measure something at equilibrium. In this case, it was the products. It frankly could have been any of the reactants or products, right? Because by the magic of my ice chart, right, I always know the change line. It's just stoichiometry, right? And so if I really want to know everything in the ice chart, what I really need to know are two things for everything, right? Because the logic of the ice chart is always that I plus C equals E. So even though there's three time frames, if I know two of them, the third one's automatic, right? If I plus C is E, E minus I is C, or E minus C is I, or you do the algebra any way you want, right? And so if you think about it in terms of the actual problem solving of it, right? Since each of those columns is fundamentally a little algebra problem, right? All I really need is the equilibrium amount of anything and the initial amounts of the reactants, and it will solve for the equilibrium amounts of everything because there's only really one unknown, which is the amount of stuff that reacted, or X as it's represented in my ice chart. So in this particular case, I converted my grams to moles because, of course, grams is good, but moles is better. And so I had the initial moles of the reactants. Implicitly, I also had the initial moles of the products. I didn't throw any in to begin with. All right. And then I measured the equilibrium amount of the water, which created one column that's a solvable algebraic equation, which simultaneously solves the other two columns, right? Because it's the same X in every column. It's the magic of stoichiometry that's really powering my ice chart. Right. And so this is about where we got at the very end of class, as you might have been nodding off, packing up, or zooming out, right? My initial plus my change is always my equilibrium amount, right? In the case of the first two columns, that really gives me an algebraic expression that I cannot solve, right? The equilibrium amount is 2.16 minus 2x. That's great, right? I had $100 and I don't know what I spent, right? Therefore, I don't know what I have. But in the product column, I started with none and I ended up with 0.366. So 0 plus 2x equals 0.366 is a solvable algebraic relationship, and it's the same X everywhere. And so in this case, X is 0.183 moles, right? Which simultaneously solves the other two columns, right? That's why the ice charts are so useful and powerful. It's not like you couldn't do all of that math without the ice chart, right? But the ice chart keeps it organized. The ice chart serves as a prompt for the things you need to know, right? And the ice chart does simultaneously do the math for everything, right? Otherwise, it would be a separate calculation to determine the final amount of hydrogen and the final amount of oxygen. Right. And so if I had 0.366 moles of water at equilibrium, I must also have left over 0.711 moles of oxygen and 1.794 moles of hydrogen. Right. Those are my equilibrium moles of everything. Right. And of course, if I'm trying to construct the equilibrium constant, which was my goal, that's what I need. I need to know what I have of all of the reactants and all of the products at equilibrium. However, units, right? My equilibrium constants are always either molarities or, in the case of gases, atmospheres. All right. And so while I did my ice chart in moles, I cannot capital C, capital A, capital not. Right? I cannot put moles into the equilibrium expression. It has to either be molarity or atmospheres. Right? If it's molarities, I have a Kc. If it's atmospheres, I have a Kp. In this case, since it didn't specify it, and they're all gases, I could have done either one. I went with Kc. So again, I turn my moles into molarities. It's moles per liter. They're all in the same 2-liter flask. Right. If I then plug them back into my equilibrium expression, I get the magic ratio of 0.117. Right. Yes, no. That is where we ended up on Monday, but we did sort of rush through at the last minute as we were running out of time. Right. Now, since I do ultimately need either molarity or atmospheres, you might ask, why didn't I go to molarities or atmospheres at the beginning? The answer is no particular reason, right? The thing about the ice chart is, right, my ice chart is really driven by the stoichiometry, right? Because what makes the ice chart go is the change line, right? Because that is the relationship between the hydrogen, the oxygen, and the water. I can start with whatever I want. There's no relationship. I end up with whatever I end up with. The only thing that's 2 to 1 to 2, right, is the stoichiometry of the reaction, meaning it's the stuff that reacted, which is what the change line really represents, right? And so stoichiometry is moles, 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 right? Which means my ice chart can't be in grams because there's no direct mass relationship represented by my balanced equation. I mean, I could calculate it for what the relative masses are relative to the relative moles, but that's not the way balanced equations are written. 2 to 1 to 2 is not grams. 2 to 1 to 2 is moles.
I have a quick question.
Yeah.
What's the difference between KC, KP, and KE again?
Units.
And specifically, what were the differences?
KC is molarity, KP is atmospheres, KEQ is both.
So for KEQ, is it like if it's gaseous, you use atmospheres? If it's not, then you use
Use the
molarity?
preferred units for whatever the state of
Okay,
matter
cool.
is.
Thanks.
Now, as I was saying, right, I can't use grams because my balanced equation isn't in grams. I don't, however, have to use moles necessarily if I'm using something that's directly proportional to moles. So in fact, as I sometimes say, my ice chart could be in anything molesish, right? Meaning it could be in molarity. After all of those things are in the same beaker, right? So the moles are related 2 to 1 to 2, but so are the molarities. Because after all, to get to molarities, all I did is divide everything by the same 2-liter flask. Similarly, since they're all in the same 2-liter flask and they're all at the same temperature, I could calculate the pressures, right? Pressure is really moles, 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 right? So I could construct my ice chart from the beginning using either moles or molarity or atmospheres, right? There's no functional difference in terms of the problem solving. There are some times, as you'll see in a week or so, why I prefer the moles to the molarity, all right? But in general, it doesn't really make any difference. And in the end, when I get to K, it has to be either molarity or atmospheres. Right? And so I could have done it in molarity if I wanted, right? I had the moles, divide them by liters up front. There's my initial amounts in molarities. There's my final amount in molarities. It's a slightly different ice chart, which gets me to the same point, right? The number's different, but the value's the same, right? Because the unit's different, right? X is now 0.0915 molar instead of 0.1833 moles. If I solve it and plug it in, I get exactly the same answer, all right, for KC. And so I can do it either way. I usually do it whatever I consider easiest for the particular problem. There is one particular case where one way is preferable, but for the most part, it's just personal preference. In the end, I have to get to either molarity or atmospheres. So it doesn't really matter until I'm ready to plug into K what I have. All right, and in a nutshell, those are what I would term, again, equilibrium problems of the first type. I'm trying to find K, right? The first problem we did is typically not how it goes in the lab, right? In that case, I threw everything in a beaker, I let it react, and then I measured the concentration of everything at equilibrium. Not usually the way it goes, right? That's harder measurements than I need to do, right? The easy thing to measure is the initial amount. It's harder to measure it after the reaction has happened because you have to measure without separating it for reasons we'll get to in a minute. But right, the way it would normally go if I'm trying to determine an equilibrium constant, measure what you throw in the beaker and find one thing to measure at equilibrium. Right. And that really is it, right? I could do it, 10 slightly different ways, but ultimately they're all the same basic structure. I measure what I start with, I measure something at equilibrium. The ice chart tells me what everything at equilibrium it is, and there's my ratio, and I get the equilibrium constant. Right? And so it's only a couple examples. The homework will give you more, but for equilibrium problems of the first type, that's it. Now, I could have KPs and KCs. We'll talk more about that in a minute. But in the end, I measure what I start with. I measure one thing at equilibrium. The ice chart works it all out, and I have the K equation. Most of what we do with equilibrium revolves around types of reactions that are known and well studied, right? For those types of reactions, the equilibrium constants are frequently known, right? And so most of the problems we solve, not all, but most, would fall into what I've been calling equilibrium problems of the second type, which is I've already determined Kc, right? As long as I don't change the temperature, that Kc should be constant. It's the equilibrium constant after all, right? And so I can use it now to determine where my reaction reaches its balanced ending, or in a shorter phrase, where my reaction reaches equilibrium, right? Because again, now the world is not limiting reactant problems. I'm still limited in how much product I can make, but that limit is not based on running out of something. It's based on where my equilibrium falls. If I've got a really big equilibrium constant, like really, really big, it ends up acting like a limiting reactant problem. I virtually run out of something, right? On the other hand, they're not all big. And so if I have a moderate equilibrium constant, I'm going to have a lot of reactants left, and I'm going to have products, right? And my limit on how much stuff I can make is now the equilibrium constant, not the limiting reactant, right? And so an equilibrium problem of the second type works something like this, right? Somebody already measured the equilibrium constant for my reaction in a manner similar to what we just did. I now want to do the reaction, right? And I want to know how much product I can make, right? In some sense, this is the opposite of what we were doing before. Before I was trying to find the equilibrium constant, now I know it. On the other hand, I would argue it's exactly the same thing we were doing before, because of course, all equilibrium problems have three parts. The only thing different is what I know up front, right? But in the end, I'm still solving for one unknown, presumably. It's just a different unknown than I had before. Although actually, it's the same unknown in a slightly different equation, right? So again, all equilibrium problems have three parts. This is no different. As soon as I even sense there's an equilibrium problem going on, and I can get as far as the second word before I know that, it says Kc, right? I start constructing my equilibrium problem based on my standard three parts, right? And again, the first and most important is always the balanced equation. because the balanced equation immediately, without thinking, leads to the equilibrium expression. Right. My only difference here, unlike the prior problem, is I have a value for K. Right? It's the same ratio of products to reactants, but now K is not unknown. It's 4.1, or it's 4 times 10 to the minus 6. Right. My ice chart is still my ice chart. And again, as I like to say, without thinking, virtually, I can immediately plug in the change line, because the change line is really just stoichiometry. Right? I don't have exact numbers for it, but symbolically, it's always -2 hydrogens, -1 oxygen, and +2 waters. Since I don't know the exact numbers, call it X, the ratio holds, right? And then it's really just a question of which things I know and which things I don't know. In this case, what I was given is, again, the thing I should know all the time. Right. I know what I started with. Right. There's almost no excuse for not knowing what you started with. The only exception to that is if you're trying to analyze a sample of something, right? If I go pull a sample of swamp water from, well, pretty much anywhere on campus, we're surrounded by swamps, excuse me, wetlands, right? If I want to analyze the swamp water, I don't know what's in it when I start. And so the only time I really don't know is if I'm trying to analyze somebody else's sample, in that case, God's, right? If I'm doing a reaction in the lab, there's no excuse not to know what I throw in the beaker. Right. And so in this case, I had the initial amount of hydrogen and the initial amount of oxygen in these somewhat artificial units of mass. You generally don't weigh gases, but I'm not quite ready for KP. All right. Again, I can do it in moles or I can do it in molarity. Right. Or I could do it in atmospheres. Right. In this particular case, right, because ultimately I had to get to molarity anyway, I did the ice chart in molarity. And so I knew the initial amounts. I know nothing about the equilibrium, right? I do not know the equilibrium amount of hydrogen or oxygen or water. Although, again, because I plus C equals E, as soon as I filled in the I line and the C line, I know what the E line is, at least symbolically, right? Because I plus C is always E. So I knew I had 0.827 molar hydrogen. I'm going to lose 2x. That leaves me with 0.827 minus 2x. All right. I know I started with 0.0533 molar oxygen. I'm going to lose x. So I end up with 0.0533 minus x. And of course, I started with no water and I made 2x. So I end up with 2x water. All right. I would know everything if I knew any one of those equilibrium amounts, but that would really make it a equilibrium problem of the first type. All right. In fact, I don't know any of those equilibrium amounts. I do, however, know what the ratio of all of them is, right? Because that's what my equilibrium constant actually represents. All right. Kc or Kp or Keq is just the ratio of the products to the reactants raised to their respective stoichiometries. And so I don't know any one of them. I do, however, know the ratio of all three of them. And that's as good as knowing any one of them, right? At least mathematically, because I still have one equation with one unknown. That should be solvable. With me so far? This is my favorite part of the whole semester. This is your chance to lie to me. So it's also a silly lie. There's no point in this lie. Let's see if you can avoid the lie. So let's say that is your homework problem. What would you do? How would you solve that? Anyone? Calculator, specifically meaning?
Use a calculator.
In what way use the calculator?
Input the numbers.
Input the numbers. Yeah, but that only works if you have a specific type of calculator. Anybody?
You can use like a quadratic calculator online.
Yeah, I mean, you need a graphing calculator or something with a solving routine. You can't just plug X's into your average calculator. I assume that's what Leland was getting at. He's so used to his graphing calculator, he doesn't really think of it as being special. Right? If you have a, what? Go ahead.
You can use Excel. Excel has a solver.
Well, you could use other solving routines. God bless you for not actually lying to me this semester. You could also, well, there are ways you could algebraically solve it. Your problem is it's a third order polynomial equation, so it's not as straightforward as, I'll get to that. Yes, you can, right? But you can use a graphing calculator if you have one, right? All the graphing calculator does is graph it, and it's really just looking for the intersection, right, of the pieces of my graph. You can use different versions of the graphing calculator, right? There are solving routines that you can use as plugins in Excel. There are also websites one could use. There's one like, it's either Solvit or solvex.com. The one I'm familiar with is Wolfram Alpha. And usually many students are familiar with that. For some reason, they will never fess up to using it. That's what I meant by people tend to lie to me, right? And frankly, that's perfectly legitimate. Your math instructor might say otherwise, right? And in fact, at least one of the math instructors around here tells everybody that Wolfram Alpha doesn't know what it's doing and yada, yada, yada. And of course, you know, there's approximations built into the code. It's not perfect. But you know what? Neither is my data. It's not a math course. I don't need an exact solution to that, right? Because I have a limited number of sig figs to begin with. Technically, if you look at my K equation, I only know the equilibrium constant here to 1 sig fig. Right? Even my concentrations, if you go back to the numbers, I only know them to 2 or 3 sig figs. Right? I don't have an infinite number of sig figs. I don't really need an exact solution. So Wolfram Alpha won't give you an exact solution. I don't need it to be exact. I only need a couple sig figs. It'll work. Your graphing calculator won't give you an exact solution in most cases. I mean, for a simple polynomial, it will, but the higher the order, the more approximations there are to avoid stack overflows and the rest of it, but you could do it. On the other hand, knowing this is experimental data and limited accuracy is enough, I can actually simplify this. People hate this. I don't know why. It's a perfectly legitimate calculation trick, which also works in biology, physics, everywhere except math, right? Because again, in most cases, not all cases, an applied math course would understand it, right? In math, the tendency is to think of these numbers as exact things. In any science, my numbers are not generally exact. I mean, sometimes they are, right? H2 is exactly 2 hydrogen atoms, but except for when I'm counting, most sciences, The numbers are not exact. If I weigh something, there's a limited number of sig figs. If I measure a volume, there's a limited number of sig figs. If I measure a pressure, there's a limited number of sig figs. And so if I recognize that, right, I have a limited number of sig figs, I don't need an infinitely accurate answer. It's a waste of my time trying to find one, right? If I find an answer that has 9 sig figs in it, 7 of them aren't significant, right? There's no point in calculating those last 5, right? And so this is a perfectly legitimate, I'm going to go with trick, mathematical method in any experimental course because I have limited accuracy to begin with. And so what I'm going to do is assume x is less than 0.0533. I am not making x 0, as some people like to interpret this. Because of course, if I'm assuming x is 0, my answer is x is 0, which basically tells me nothing happened in the reaction. I'm not assuming x is 0. I'm assuming x is small relative to 0.0533, which is a starting concentration. If you think of this in terms of the underlying chemistry, what I'm assuming is that not a lot of stuff reacts, right? Those 2 amounts in the denominator are the initial amounts of the reactants. And so my fundamental assumption here is that the amount of reactants doesn't change very much. This is sometimes a horrible assumption, right? If this were nearly a limiting reactant problem, most of the reactants would react, in which case this assumption is going to fail horribly. On the other hand, it works more often than you might think. And if it works, it saves me a whole lot of trouble. I don't even need a graphing calculator.
I have a quick question.
Yes.
I had trouble in Chem 1 like deciding when to make that assumptions. Like when.
Don't ever try to decide.
Okay.
There's no reason to try to decide. I don't know if this is going to work now. I'm going to find out how good an assumption is. In the somewhat always imperfect metaphor, you can assume you can fly. Step off the building, you'll find out if it's a good assumption. In this case, nobody breaks a leg. Apologies to Tiger Woods, it might be too soon to mention broken legs. All right, trigger warning, all right? If it doesn't work, I'm gonna know in a minute, right? This again is where the internet is your enemy. The internet will tell you all kinds of fancy little back of the envelope calculations you can do to decide whether to do this. It takes less time to do this than it told me to tell you not to try to figure out whether to do this, right? I always do it because I'm just that lazy. However, I also have to justify it in the end, right? And so if I assume x is much less than 0.0533, what that means is x doesn't change 0.0533. Why did I pick 0.0533? Because 0.827 is bigger, right? If x isn't going to change 0.0533 very much, it's not going to change 0.827 very much either, right? 0.827, you know, is 14 times bigger, 15 times bigger. All right, if I do that, again, I'm essentially assuming the amount of reactants has barely changed. My somewhat complicated looking, annoying polynomial equation, right, ends up being very simple. Again, I'm not assuming x is 0. If I was assuming x is 0, what about the x in the numerator? I end up with nothing left to solve. I'm assuming it's just small. I used to pick on Bill Gates. You can tell how old this slide is because Bill Gates is now worth like $120 billion because he needs more money. All right. But, you know, if Bill Gates, let's pick on Bill Gates. We can hate on Bill Gates. He's rich. All right. If Bill Gates is worth $72.5 billion, he gives you $100. What's Bill Gates worth? $72.5 billion. Here's where the hate comes in. Bill Gates is worth $72.5 billion. If he gives you $1 million, what's Bill Gates worth?
72.5 billion.
$72.5 billion. In fact, he can give you $10 million and his net worth does not change. Bastard. Right? Because again, unless he balances his net worth to the nearest dollar, you know, Scrooge McDuck style, it's beyond where I measured it because he's not exactly 72.5 billion. It's the same issue here. What I want is X to be small enough that it doesn't change the number I subtracted from. Right? And so I have a built-in test for whether or not it was a good assumption. I made the assumption, I calculate the answer. The answer itself tells me whether or not the assumption was good. I assumed X was small relative to 0.0533. There's X, subject to the assumption. It either is or is not much less than 0.0533. You can see the value of doing it, right? I went from a polynomial equation where I needed some kind of sophisticated software to solve it to an equation I could solve by cross-multiplying and taking a square root. Right, I can do that on a dollar store calculator. Right, I could virtually do it in the back of an envelope with a pencil, depending on how good you are at square roots. Right, and so I end up with a value for X. Now, rather than before, I have to decide whether that was a good idea. And so I ask you, was that a good assumption? Is X much less than 0.0533? We should vote. It's kind of hard for the Zoom people to vote, but feel free to unmute yourself and shout something out. Is X less than 0.0533? All in favor of yes, shout it out.
Yes. Yes, it is.
I got like 2 people on the Zoom. Of course, everyone else went out to breakfast about 10 minutes ago. All in favor of no? I got no no's. No, thank you. Someone came back from breakfast. No, I have one person who said no, and apparently like 5 people who said yes, and everyone else is sleeping. The answer is no, or yes. The better answer is it depends, right? It depends on whether Bill Gates is Bill Gates or Scrooge McDuck. Right, because if you think about what I'm doing with the number, I'm subtracting it from 2 other numbers. In fact, if I do that math, I do notice the difference. Right, it is not like Bill Gates giving you $100, which is 5 digits to the right of his net worth. Right, 0.0533 minus 0.000191 is 0.0531. It's not the same. On the other hand, it's not a huge difference. And so whether or not it's a good assumption partly depends on how accurately I feel I need to know the number. It's a sig fig issue, right? I still have 2 sig figs. I no longer have 3 sig figs, right? And so whether it's a good assumption or not depends on whether I can live with 2 sig figs. Right. This is why ultimately it is neither necessary or a good idea to try to decide up front. It's too complicated to make the decision. It's easier to try it and then decide. At this point, looking at the number, I decide, can I live with 2 sig figs? If the answer is yes, then it was a good assumption. If the answer is no, back to Wolfram Alpha or your graphing calculator or Excel solver or whatever other trick you'd like to use to solve my 3rd order polynomial. All right. There is in the book and often on the internet, there is a back of the envelope type justification after the fact for whether it's a good assumption or not. And, you know, it's the 5% rule. Right. This is a completely arbitrary standard. It's kind of the 2 sig fig standard. Right. If I assume X is small and the X I get is less than 5% of the number I was comparing it to, right, 1/20th, I take it to be a good assumption. If it's more than 5%, I do not, right? It's really the 2 sig fig rule. But if you want an actual mathematical way to justify the assumption, that's it. So 5% of 0.0533 is 0.00267. Right? So any X value less than 0.00267, I would consider it to be a good assumption that it's small. Anything greater than 0.00267, I would take to be a bad assumption. It's really, again, a 2 sig fig rule.
I have a question.
Hang on. Right.
Okay.
So again, in this case, it's close, but not that close. Right. It's not so infinitesimally small, right, that I don't notice it at all, but it is small enough that I barely notice it. It really only makes a difference in the 3rd sig fig. Yes. What's your question?
So there's like negative values of X that work in that solution. What do those mean?
The question was, what do negative values of X mean? Negative values of X mean the reaction is moving backwards. Right? If you look at the ice chart, it assumes the reaction is moving forward. That's why it was minus 2x, minus x, and plus 2x. If x were negative, it means you have fewer products at the end or more reactants. There is no reason why x cannot be negative. Except
So-
in this case, there is.
Oh,
But it has nothing to do with x itself. X can be either positive or negative. What you cannot have is a negative amount left over. Right? You can't have negative moles of something. In this case, if x were negative, because my water is 2x, I would have negative 3.8 times 10 to the minus 4 molar water. That makes no physical sense. You cannot owe the universe, right, water. However, I do not base the assumption on whether x is negative or positive. If I had started with water as well as hydrogen and oxygen, there's no reason why x might not be negative. Because I fundamentally assume the reaction was going left to right. Reactions go both ways. And so the decision over which route to take is based less on what the value of that number is and more on what happens in my ice chart. Right? I cannot have a negative amount of stuff. I can, of course, have a negative change. I do it all the time. I had $100. I went to the mall. I only have 80. My change in dollars was negative 20. I defy you to hand me negative $20. I dare you, because that means you have to steal it from me, right? It all goes back to the ice chart and whether it makes any physical sense to have a negative root. In some cases, I think it was somebody in here, the Belousov, I can never pronounce the second word, reaction. There are reactions that have more than one solution. They have bistable endpoints. Right. In general, most of the time, one of the roots makes no chemical sense, even though it makes perfectly good mathematical sense. There's no reason why the negative root isn't correct mathematically. It doesn't make any sense whatsoever in my ice chart. You can send me an invoice. That doesn't mean I'll pay it. Yes, no. Now, obviously, there are times that does not work. All right. In which case, you're going to have to do the math. But, as I'm fond of saying and will continue to say, it is always worth trying. because it takes less time to figure out whether or not it's going to work by doing it than it does to try to make a decision up front. And it works more times than it doesn't, you will see. And when it does work, it saves me a whole lot of trouble trying to solve the thing. Now, you know, that's partly a lie, right? In the sense that depending on how friendly you are with your calculator or your various websites, right, it doesn't take a whole lot of time necessarily to solve one of those equations, but it is tremendously simplified. And even if it's not absolutely necessary in a mathematical sense, it's a useful trick like in lab or something if you're just trying to get a rough estimate of what the answer is, right? I don't have to go and crunch all the numbers. I make the assumption, I solve it, and I have a ballpark figure, right?
If you try that method and it doesn't work, how do you know that it didn't work?
My 5% rule would have failed. If X was larger than 5% of the number I compared it to, it did not work.
Okay.
It's too big a difference to justify. All right. Now, if it doesn't work, you're going to have to do the math, right? In some sense, since we don't have any tests, I almost don't have to make this promise anymore, right? But in general, we don't see anything in here that is more than quadratic in the end, right? And so to that end, I would not assume, since you're not required to have a graphing calculator, all right, I would not assume that you could easily solve a third or a fourth or a fifth order polynomial equation. And so we won't see anything that's more than quadratic because, as you probably know, I can fairly simply solve a quadratic equation using the good old quadratic formula, right? If I put my quadratic equation in the standard form, which is some coefficient times x squared plus some coefficient times x plus some coefficient equals 0, the two solutions, because a polynomial equation has as many solutions as the order of x, my two solutions for the quadratic are negative b plus or minus b squared minus 4ac all over 2a, right? And so I'm going to do this problem, even though I only have 3 minutes. Here's a case where my assumption does not work. Now, I kind of knew that up front. You don't have to. I'm just always going to try. Right here, this is my high reaction. I mix hydrogen and iodine. I make high hydrogen iodide. All right. And I know the equilibrium constant up front. It's 54.3. Right. So like all equilibrium problems, same 3 parts. My balanced equation is hydrogen plus iodine makes for 2 highs, hydrogen iodides. They are, again, all gases. It could be Kp or Kc. I was given Kc, so it's going to have to be concentrations. Once I have the balanced equation, I can write the equilibrium expression and construct the ice chart. There's my ice chart. I was given the molarities of the 2 reactants. The change line I always know because it's always just stoichiometry, so minus x and plus 2x. And of course, I plus c is always E. So 0.0025 minus x equals E. Right, 0.005 minus x equals E. And 0 plus 2x equals 2x. All right, and so again, I have my ice chart. I have one unknown, x. I don't know the equilibrium concentration of everything, but again, like last time, I do know the equilibrium constant that goes with my equilibrium expression. All right. And again, it's a slightly messy polynomial equation. All right. And as I'm fond of saying, even though I know it won't work, and I told you it won't work, it takes less time to find out it won't work than to decide. And so I'm going to assume x is less than 0.0025, right? Because that makes both of the x's in the denominator insignificant. If I do that, again, all I have to do is cross multiply and take the square root, right? If I do that, I get 0.0130, right? This is a failure because, again, my comparison, and it is fundamentally a comparison, was x to 0.0025, right? And so if I cling and I always do, to my arbitrary 5% rule, because as I'm fond of saying, there's no point in having an arbitrary rule if I don't use it, right? My standard of small is 5% of 0.0025, which is 0.000125. That is my standard of small. If I'm smaller than that, I'm small. If I'm bigger than that, I'm big. As you can see, 0.0130 ain't even close. In fact, not only is it not less than 5% of 0.0025, it's not even less than 0.0025. All right. And so the assumption doesn't work. It took me 30 seconds to find that out. That's 30 seconds I'll never get back. But the number of times it does work outnumber the numbers of times it doesn't work, right? And so I save in the long run. Since it doesn't work, I'm going to have to do it the long, hard, honest, true way, which means either solve the quadratic, as that slide does, or of course, plug it into your graphing calculator, or plug it into Wolfram Alpha, or plug it into whatever equation solving routine you have on your phone these days, if you do. Engineers might, future engineers probably should, although again, some of my colleagues frown upon such things. But hey, there's no point in fighting the technology. Right, if I'm going to do it the long, hard, honest, true way with the quadratic equation, I need to get everything in standard quadratic form. All right, which means a number times x squared plus a number times x plus a number. All right. And then again, if I do this, I now get two positive roots. Right, and again, mathematically, they are both fundamentally correct. From a strictly mathematical sense, both of those numbers solve the original equation. But as we were saying before, and we're over time, so I'll leave it at this, right? Only one of them makes sense in the context of my ice chart, right? This is my ice chart. If I'm going to put them both in there, only one of them makes sense. If I put the 0.005736 in there, I get negative amounts for the hydrogen and iodine. Right. So in general, if I have multiple roots that solve the K equation, right, try them all in the ice chart. The only one or ones, typically it's one, right, that works is the one that makes chemical sense, which is the one that does not give you some kind of physical impossibility in the ice chart. Right. And so I throw out x equals 0.005736, even though it's a positive root, because it gives me a negative final amount, right? And so the other root is my correct root, and I am done, albeit 3 minutes late. Questions or problems? Only 500 more equilibrium problems to go, and we will be experts. Happy hump day. I will see you on Friday.
I have a
Thank you,
question,
Professor.
Professor.
Yes.
So why can we use atmospheres as a unit of concentration for gas? I just wanted to clarify that.
As opposed to pascals?
Well, like, why does pressure work as a unit of concentration? Like, why does that tell us?
Pressure is directly proportional to the number of moles. In fact, pressure is directly proportional to the number of moles per liter. And in ideal gas sense, P equals N over V, which is molarity times RT.
Okay, and so is that how we would use it in the ice chart as well, using the ideal gas relation to make the stoichiometric conversions?
Well, typically we use the ideal gas relation. In a more global sense, you could use the van der Waals equation or something for the pressure, but the same thing applies. The pressure is effectively the concentration of the gas because it is directly proportional to the number of moles.
Okay, but like, what value would we use in the ice chart for
What do
that?
you mean?
Like you said, we could use
Whatever the pressure is,
Okay, just the pressure.
just the pressure.
Okay. I thought we would have to factor in moles somewhere, but since it's directly proportional, it works.
Pressure is moles. I mean, it's directly proportional to moles in the same way that molarity isn't moles, it's moles per liter. Pressure isn't moles, but it's directly proportional to moles. And so stoichiometry works the same. I mean, 2 atmospheres of hydrogen plus 1 atmosphere of oxygen will give you 2 atmospheres of water.
Okay. Thank you.
Yep.
Have a good one, Professor.
Yep. See it.